The determinant formula for area. Welcome, everyone. Let's begin our lesson on a very useful tool in coordinate geometry. Now, you might remember from your previous studies in coordinate geometry that you learned how to calculate the area of a triangle whenever the coordinates of its vertices were provided to you. It was a bit of a manual process back then. However, as we move into grade 12, we are going to introduce a much more elegant way to simplify this entire process by using determinants. Instead of dealing with messy, long algebraic strings that are difficult to remember, this new approach provides us with a much more structured and concise way to represent and calculate the area. This will make our calculations much more organized as we move into the next slide to see exactly how we transition from the old formula to this new method. Understanding the transition. Now, before we dive into the new method, let's take a moment to look at what you already know. If we look back at our previous lessons in coordinate geometry, you might remember that calculating the area of a triangle with vertices P with x sub 1, y sub 1, Q with x sub 2, y sub 2, and R with x sub 3, y sub 3 usually involves this long-form formula. Area equals 1/2, inside absolute value bars, of x sub 1 times the quantity y sub 2 minus y sub 3, plus x sub 2 times the quantity y sub 3 minus y sub 1, plus x sub 3 times the quantity y sub 1 minus y sub 2. Now, while this formula is mathematically perfectly correct, let's be honest, it can be quite a headache to use during an exam. It is very easy to lose track of your parentheses or make a small mistake with a negative sign when you're working through all those terms manually. This is exactly why we are transitioning to a new approach. As we will see in the next slide, by using a determinant, we can organize all these coordinates into a neat, matrix-like structure. This makes our work much more systematic and significantly reduces the chance of those frustrating calculation errors. The determinant representation. If we have a triangle with 3 vertices, which we'll call x sub 1, y sub 1, x sub 2, y sub 2, and x sub 3, y sub 3, we can express the area, which we'll denote by the Greek letter delta as 1/2 times the determinant of a 3x3 matrix. Now you might be wondering how we get from 2-dimensional coordinates to a 3x3 structure. Let's break down this determinant structure together. First, look at the first column. This is where we place all of our x-coordinates from our 3 vertices. Moving to the second column, we list all of our y-coordinates. Finally, you'll notice the third column. This column simply contains the constant one for each row. This might seem a bit strange at first, but it is actually a crucial step. We add this column of ones to make the matrix a square 3x3 matrix. This is mathematically necessary because we can only calculate the determinant of a square matrix. Now that we've seen why the old algebraic formula can be a bit messy and prone to errors, let's look at the beautiful way we can rewrite it using a determinant. In the next slide, I will show you exactly how we expand this structure to perform the actual calculation. Step-by-step calculation process. Now that we understand the structure of the determinant from the previous slide, let's walk through the actual procedure. Finding the area isn't just about plugging in numbers, it's about following a systematic process to ensure accuracy. First, in step 1, you need to set up your determinant. You'll take the coordinates of your 3 vertices and place them into the rows of the determinant, just as we saw in the formula. Crucially, remember to keep that 1/2 factor outside the determinant from the very beginning. Moving on to step 2, we need to expand the determinant. We usually expand along the first row to make things easier. When you do this, you'll multiply the first x-coordinate by the determinant of the remaining 2x2 matrix, then subtract the product of the first y-coordinate and its corresponding 2x2 matrix, and finally add the product of our constant, 1, and its remaining 2x2 matrix. Specifically, it looks like x1 times the quantity y2 times 1 minus y3 times 1, minus y1 times the quantity x2 times 1 minus x3 times 1, plus 1 times the quantity x2 times y3 minus x3 times y2. In step 3, your task is to simplify the expression. This is where you perform all the multiplication and subtraction inside those brackets. It's a great place to slow down and be careful with your arithmetic. Finally, in step 4, you apply the scalar. Once you have a single numerical value from your expansion, multiply that final result by 1/2 to obtain the actual area. In the next slide, we are going to put all these steps into practice with a concrete numerical example, so keep this process in mind. Practical example. Now that we have understood the theory and the structure of the determinant, let's put it into practice with a real-world application. Imagine you are a land surveyor tasked with mapping a triangular plot of land on a coordinate grid. The corners of this plot are located at 3 specific points: point A at 1, 1, point B at 3, 4, and point C at 5, 2. Our goal is to find the total area of this plot using the method we just learned. Let's walk through the solution step by step. First, in step 1, we need to identify our coordinates clearly. We'll assign our first vertex x1, y1 as 1, 1, our second vertex x2, y2 as 3, 4, and our third vertex x3, y3 as 5, 2. In step 2, we substitute these values into our determinant formula. We start with 1/2, and then we set up our 3x3 determinant. In the first row, we place 1, 1, and 1. In the second row, we place 3, 4, and 1. And in the third row, we place 5, 2, and 1. Now, for step 3, we expand the determinant along the first row. This is where we apply the expansion technique we discussed in the previous slide. We take the first element, 1, and multiply it by the determinant of the remaining 2x2 matrix, which is 4 times 1 minus 2 times 1. Then, we subtract the second element, 1, multiplied by the determinant of the remaining elements, which is 3 times 1 minus 5 times 1. Finally, we add the third element, 1, multiplied by the determinant of the remaining 2x2 matrix, which is 3 times 2 minus 5 times 4. Moving to step 4, let's simplify these terms. Inside the first bracket, 4 minus 2 gives us 2. In the second bracket, 3 minus 5 gives us negative 2. And in the third bracket, 6 minus 20 gives us negative 14. When we multiply these out, we are left with 1 times 2, minus 1 times negative 2, plus 1 times negative 14. This simplifies further to 2 plus 2 minus 14. Finally, in step 5, we calculate the final result. 2 plus 2 is 4, and 4 minus 14 leaves us with negative 5, so our calculation gives us negative 5 square units. Now, a quick note here. As you might realize, area cannot be a negative value. In geometry, we always take the absolute value of our result. Therefore, the actual area of the plot is 5 square units. We will discuss the significance of this negative sign and the use of absolute values in much more detail in our next subsection. Keep this in mind as we move toward our final takeaways. Key takeaways. First, remember that the determinant method is not just another formula to memorize, but a highly systematic and organized way to calculate the area of a triangle when you are given its vertices. It replaces those long, messy algebraic strings we saw earlier with a much cleaner structure. The core formula you need to master is delta equals 1/2, multiplied by the determinant of a 3x3 matrix, where the first column contains x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, and y sub 3, and the second column contains y sub 1, y sub 2, and y sub 3, followed by a third column consisting entirely of ones. It is crucial to remember why that third column is there. It always consists of ones to facilitate the 3x3 determinant expansion, making the matrix square and solvable. Finally, a very important reminder. Once you have finished the expansion and simplified your terms, the result of that determinant expansion must be multiplied by 1/2 to obtain the actual area. Now that we have worked through that practical example, let's pause and summarize the key takeaways from today's lesson to ensure you have a solid grasp of the concept. In our next slide, we will look at some common pitfalls to watch out for, so pay close attention to those specific steps. Common mistakes to avoid. First, please be mindful of forgetting the 1/2 factor. As we saw in our step-by-step calculation on the previous slides, the determinant itself only gives us a part of the value. You must remember to multiply your final result by 1/2 to get the actual area. Second, watch out for coordinate swapping. It is crucial to be disciplined with your organization. Ensure that all x coordinates are strictly placed in the first column and all y coordinates are in the second column. If you mix these up, your entire calculation will be incorrect. Third, pay close attention to sign errors during expansion. This is a classic mistake. When you are expanding the determinant, remember that the second term, the one involving y1, is subtracted. If you forget that negative sign, your final value will be wrong. Finally, do not ignore the constant column. Some students attempt to use a 3x2 matrix, but as we learned in the previous slides, a determinant must be a square matrix. You must include that third column of ones to make it a 3x3 structure, otherwise, the determinant cannot be calculated at all. Now, as we wrap up this lesson, I want to pause and discuss some common pitfalls. Even when you understand the formula, it is very easy to make small errors that can lead to the wrong final answer. Keep these points in mind, and you will find this method to be a much more reliable tool than the long algebraic formulas we used in the past.